Welcome to the series on e-learning modules on covariance. By the end of this session, you will be able to explain the meaning and definition of covariance, explain the properties of covariance, explain the interpretation of value obtained in covariance, explain the uncorrelatedness and independence, and to explain the limitations of covariance. Firstly, let us understand the meaning of covariance. Covariance is a measure of how much two random variables change together. That is, covariance provides a measure of the strength of the correlation between two or more sets of random variates. If the greater values of one variable mainly correspond with the greater values of the other variable and the same holds for the smaller values, that is, the variables tend to show similar behavior, the covariance is positive. In the opposite case, when the greater values of one variable mainly correspond to the smaller values of the other, that is, the variables tend to show opposite behavior, the covariance is negative. The sign of the covariance shows the tendency in the linear relationship between the variables. The magnitude of the covariance is not that easy to interpret. However, the normalized version of the covariance, the correlation coefficient, shows by its magnitude the strength of the linear relation. A distinction must be made between the covariance of two random variables, which is a population parameter that can be seen as a property of the joint probability distribution, and the sample covariance, which serves as an estimated value of the parameter. Now, let us define covariance. Covariance of two random variables x and y, each with sample size n, is defined by the expectation value. That is, if x and y are two random variables, then covariance between them is defined as covariance of x y is equal to expectation of x minus e of x into y minus e of y. On multiplying the terms inside the brackets, we get expectation of x into y minus y into e of x minus x into e of y plus e of x into e of y. Taking expectation inside, we get expectation of x into y minus expectation of y into expectation of x minus expectation of x into expectation of y plus expectation of x into expectation of y. On cancelling the same terms with opposite signs, we get expectation of x into y minus expectation of x into expectation of y. It can be also denoted by sigma xy. If x and y are independent, then expectation of x into y is equal to expectation of x into expectation of y. Hence, in this case, covariance of xy is equal to expectation of x into expectation of y minus expectation of x into expectation of y is equal to 0. Now, coming to the properties of covariance. Now, let us state and prove different properties of covariance. If x and y are two random variables, a and b are constants, then covariance of a into x and b into y is equal to a into b into covariance of x y. We can prove this property as follows. Covariance of a into x and b into y is equal to expectation of a into x minus e of a into x into b into y minus e of b into y, which is equal to expectation of a into x minus a into e of x into b into y minus b into e of y. By taking common terms outside, we get a into b into expectation of x minus e of x into y minus e of y, which is equal to a into b into covariance of x y. If x and y are two random variables, a and b are constants, then covariance of a into x and b into y is equal to covariance of x y. To prove this property, consider the left hand side. Covariance of x plus a and x plus b is equal to expectation of x plus a minus e of x plus a into y plus b minus e of y plus b. By taking constants outside the expectation, we get expectation of x plus a minus e of x into y plus b minus e of y. On simplification, we get expectation of x minus e of x into y minus e of y is equal to covariance of x y. The third property is as follows. If x and y are two random variables and a, b, c and d are constants, then covariance of a into x plus b and c into y plus d is equal to a into c into covariance of x y. We prove this property as follows. Covariance of a into x plus b and c into y plus d is equal to expectation of a into x plus b minus e of a into x plus b into c into y plus d minus e of c into y plus d. On simplification, we get expectation of a into x plus b minus a minus b into e of x into y plus c minus d into e of y. By cancelling same terms with opposite signs and taking constant terms outside, we get a into c into expectation of x minus e of x into y minus e of y, which is equal to a into c into covariance of x y. Covariance of a random variable with itself, that if we consider y is equal to x, then covariance of x y is equal to variance of x. Consider covariance of x is equal to expectation of x minus e of x into x minus e of x is equal to expectation of x minus e of x the whole square is same as variance of x. Hence, when we take both the variables same, we can consider variance of the distribution as a particular case of covariance. Property of symmetry states that covariance of x y is equal to covariance of y x. We can prove this property as follows. Consider covariance of x y is equal to expectation of x minus e of x into y minus e of y. It can also be written as expectation of y minus e of y into x minus e of x, which is equal to covariance of y x. Hence, covariance of x y is equal to covariance of y x. Let us prove the property of bilinearity of covariance. Let x, y and z are real valued random variables and let a, b and c are constants. Then consider covariance of a into x plus b into y and c into z is equal to expectation of a into x plus b into y minus e of a into x plus b into y into c into z minus e of c into z, which is equal to expectation of a into x minus a into e of x plus b into y minus b into e of y into c into z minus c into e of z, which is equal to expectation of a into x minus a into e of x into c into z minus c into e of z plus expectation of b into y minus b into e of y into c into z minus c into e of z. By taking constant terms a and b outside, we get a into c into expectation of x minus e of x into z minus e of z plus b into c into expectation of y minus e of y into z minus e of z, which is equal to a into c into covariance of x z plus b into c into covariance of y z. Name this as equation number 1, which is a linear function. Now, by property of symmetry, covariance of c into z and a into x plus b into y is equal to a into c into covariance of z and x plus b into c into covariance of z and y is also a linear function. From 1 and 2, we can say that covariances are bilinear. Hence, in general, if we can take up x1, x2 up to xk and yb k plus 1 random variables and a1, a2 up to ak and c are constants, then covariance of summation ai into xi and c into y is equal to c into summation ai into covariance of xi and y. If x1, x2 up to xn, y1, y2 up to ym are random variables, then covariance between summation over I is equal to 1 to n xi and summation over j is equal to 1 to m yj is equal to summation over I is equal to 1 to n summation over j is equal to 1 to m covariance of xi yj. Let us prove this property using the previous property, that is, we know that covariance of summation ai into xi and c into y is equal to c into summation ai into covariance of xi y. Suppose we take all ai's and c to be 1, we get covariance of summation xi and y is equal to summation covariance of xi and y. Name it as 1. Now, consider the left hand side. Covariance of summation over I is equal to 1 to n xi and summation over j is equal to 1 to m yj, which is equal to summation over I is equal to 1 to n covariance of xi and summation over j is equal to 1 to m yj from 1. Using property of symmetry, we can write summation over I is equal to 1 to n covariance of j is equal to 1 to m yj xi. Again from 1 we get summation over I is equal to 1 to n summation over j is equal to 1 to m covariance of yj xi. Now, again by property of symmetry, we get it as summation over I is equal to 1 to n summation over j is equal to 1 to m covariance of xi yj. Hence, we can prove the seventh property. If x, y, u and v are real valued random variables and a, b, c and d are constants, then covariance of a into x plus b into y and c into u plus d into v is equal to a into c covariance of x, u plus a into d covariance of x v plus b into c covariance of y, u plus b into d covariance of y v. To prove this, consider the left hand side. Covariance of a into x plus b into y and c into u plus d into v is equal to expectation of a into x plus b into y minus e of a into x plus b into y into c into u plus d into v minus e of c into u plus d into v, which is equal to expectation of a into x minus e of x plus b into y minus e of y into c into u minus e of u plus d into v minus e of v, which is equal to expectation of a into c into x minus e of x into u minus e of u plus expectation of a into d into x minus e of x into v minus e of v plus expectation of b into c into y minus e of y into u minus e of u plus expectation of b into d into y minus e of y into v minus e of v. A into c covariance of x u plus a into d covariance of x v plus b into c covariance of y u plus b into d covariance of y v. Now, coming to the interpretation of value obtained in covariance. Now, let us interpret the value of covariance. First is positive covariance, which indicates that higher the average values of one variable tend to be paired with higher than average values of the other variable. Next is negative covariance, which indicates that higher than average values of one variable tend to be paired with lower than average values of the other variable. Now, next is zero covariance. If the two random variables are independent, the covariance will be 0. However, a covariance of 0 does not necessarily mean that the variables are independent. A non-linear relationship can exist that still would result in a covariance value of 0. Now, next coming to uncorrelatedness and independence. Now, let us see the relation between uncorrelatedness and independence. If x and y are independent, then their covariance is 0. This follows because under independence, expectation of x into y is equal to expectation of x into expectation of y. However, the converse is not generally true. For example, let x be uniformly distributed in -1 and 1 and let y is equal to x square. Clearly, x and y are dependent, but covariance of x y is equal to covariance of x and x square is equal to expectation of x into x square minus expectation of x into expectation of x square, which is equal to expectation of x cube minus expectation of x into expectation of x square is equal to 0 minus 0 into expectation of x square is equal to 0. In this case, the relationship between y and x is non-linear, while correlation and covariance are measures of linear dependence between two variables. Still, as in the example, if two variables are uncorrelated, that does not imply that they are independent. Now, coming to the limitations of covariance. Following is the limitation of covariance. Since the number representing covariance depends on the units of the data, it is difficult to compare covariances among data sets having different scales. A value that might represent a strong linear relationship for one data might represent a very weak one in another. Hence, the correlation coefficient addresses this issue by normalizing the covariance to the product of the standard deviations of the variables, creating a dimensionless quantity which facilitates the comparison of different data sets. Let x and y be two random variables such that variance of x is equal to 2 and covariance of x y is equal to 1. Obtain the covariance of 5 into x and 2 into x plus 3 into y. To prove this result, we use the property covariance of a into x plus b into y and c into z, and covariance of x is equal to variance of x. Consider covariance of 5 into x and 2 into x plus 3 into y is equal to covariance of 5 into x and 2 into x plus covariance of 5 into x and 3 into y is equal to 10 into variance of x plus 15 into covariance of x y is equal to 10 into 2 plus 15 into 1 is equal to 35. Two random variables x and y have the following joint probability density function. F of x y is equal to 4 minus x minus y divided by 8, where 0 less than or equal to x less than or equal to 2 and 0 less than or equal to y less than or equal to 2. Find the covariance of x y. Before we find expectation and variance, we find marginal distribution of x and y. Marginal distribution of x is given by f of x is equal to 1 divided by 8 into integral from 0 to 2 4 minus x minus y dy. On integrating the function and simplifying, we get 1 divided by 8 into 6 minus 2x. By taking 2 common and cancelling it with the denominator, we get 1 divided by 4 into 3 minus x, where 0 less than or equal to x less than or equal to 2. Marginal distribution of y is given by f of y is equal to 1 divided by 8 into integral from 0 to 2 4 minus x minus y dx. On integrating the function and simplifying, we get 1 divided by 8 into 6 minus 2y. By taking 2 common and cancelling it with the denominator, we get 1 divided by 4 into 3 minus y, where 0 less than or equal to y less than or equal to 2. Now, let us obtain expectation. Expectation of x is equal to integral from 0 to 2x into f of x dx is equal to 1 divided by 4 into integral from 0 to 2 x into 3 minus x dx. On integration and simplifying, we get 5 divided by 6 expectation of y is equal to integral from 0 to 2y into f of y dy is equal to 1 divided by 4 into integral from 0 to 2 y into 3 minus y dy. On integration and simplifying, we get 5 divided by 6 expectation of x into y is equal to double integral from 0 to 2 x into y into f of x y dx dy is equal to 1 divided by 8 into integral from 0 to 2y into integral from 0 into 2x into 4 minus x minus y dx dy. By integrating the terms in the bracket and simplifying, we get 1 divided by 8 into integral from 0 to 2y into 16 divided by 3 minus 2 into y dy. On integrating the function with respect to y and then simplifying, we get 2 divided by 3. Hence, covariance of xy is equal to 2 divided by 3 minus 5 divided by 6 into t divided by 6. On simplifying the equation, we get minus 1 divided by 36. Now, finally coming to the summary. Here's a summary of our learning in this session, where we have understood the meaning and definition of covariance, the properties of covariance, the interpretation of value obtained in covariance, the uncorrelatedness and independence, and finally the limitations of covariance.